Alrighty, let's see. Okay, so it's a PV diagram. You gotta love this one, right? So the temperature here is 400 kelvins, right? And it says calculate the maximum temperature of the gas during this cycle. Well, the maximum temperature is going to be the one farthest from the origin, so that's here, right? Notice that our volume is 2 liters, right? This is 2 times 10 to the minus 3 liters, and here it's 8. So we have quadrupled the volume without changing the pressure, right? So figure out what that's going to do to the, you could use the combined gas law, right? PV over T is equal to PV over T, right? For the same number of moles, right? And you know the pressure of the volume, right? And then here you know the pressure and the volume, and you can figure out the temperature, okay? Hopefully you don't need to use this. You can just figure out that if you increase the volume by a factor of 4, that has a predictable effect on the temperature, okay? Let's take a look at the next page here. Okay, so find the work done by the gas for AB, right? So for this guy, you're just going to do work is pressure change in volume, okay? And you can read the pressure off the graph. You can figure out the change in volume. Be careful about the axes of the graph, right? Remember, this is 10 to the minus 3rd cubic meters. That's 10 to the 5th pascals, right? And then the next question says, find the change in internal energy of the gas. There's 2 ways to do this. You could use this, right? U is 3/2 nRT, right? So change in U is going to be 3/2 nR times the change in temperature. The only problem with that is that we don't have the number of moles of gas, okay? But you can find the number of moles of gas because don't they tell you a pressure here? Don't they tell you a volume? And don't they tell you a temperature, right? So if PV is nRT, right, then N is going to be PV over RT, right? Okay, so that is one way to do this question, right? Which is find the change in internal energy of the gas. But you know this formula here. I mean, I'm figuring this out now, right? If U is 3/2 nRT, and if PV equals nRT, right? Then doesn't U also equal somehow 3/2 PV, right? So change in U is equal to 3/2. 3/2, that's a 2, right? P delta V, right? And we're talking about AB, right? Which is that cycle that goes, whoops, goes like this, right? Then it goes, and then it goes, what? A, B, C, right? Okay, so, it's only 1 mark, right? And it's funny because in the mark scheme, they just show that. So just use that, okay? Then figure out the thermal energy transfer to the gas. For this guy, you can use this. Q is change in U plus work, right? So you figured out the work. This is work. This is change in U. You must use the operator of addition to figure that out, okay? The answer is between 7,000 and 8,000 for this, right? The answer for this guy is between 2,000 and 5,000, right? And this answer is about between 4,000 and 5,000, okay? So anyway, now we've got the total energy transferred. By the way, this is the Q from the high temperature reservoir, right? Okay. Then it says the work done during the isothermal compression, right? So it's what is it? It's like, right? And it's then it's 1. There's our isothermal compression, A, B, C, right? It's 1390. So that's this guy here. Okay, done on the gas. So we're compressing the gas. Determine the change in entropy of the gas. Well, entropy is Q over T, right? Okay, and in this case, let's see, I think we're compressing it, so I think heat is going to flow out, right? Okay, so the Q is change in U plus work, right? Okay, but this is done on the gas, right? So it's negative work, so we go negative 1390 equals, and then remember this is 0 because an isothermal compression is the same temperature. If the temperature doesn't change, the internal energy doesn't change. So I think you can show that this much heat flows out of the gas, and then I think you know the temperature of this entire cycle because A and C are the same temperature, right? They tell you the temperature of A at the beginning, right? So then it says determine the efficiency of the cycle ABCA, right? Okay, so remember on this side here, you figured out the work done by the gas, yeah? Okay, here they're telling us that the world does 1390 joules back on the gas, right? Okay, so the net work is going to be whatever the answer was for B part 1, this work, right? Work by the gas. It's going to be that work minus 1390, right? And then the heat that flows in is the answer to this question here, okay? Thermal energy transferred to the gas. That's in the denominator, okay? So your thing is going to be the work done by the gas minus the work by the gas, right? Minus the work done on the gas over the answer to B letter 3I, right? Okay, B, I. Okay, that'll be your efficiency. And it is between 20 and 30%, okay? And then state, I love state, just yes or no, right? Where the efficiency of a Carnot engine operating between the same temperatures as those operating in cycle ABCA would be greater than, equal to, or less than the efficiency in D. Okay, well, I'll give you a clue. Okay, Carnot engines are the most efficient possible. This engine is not a Carnot. Okay, yeah, is that enough? This is, by the way, a very stupid question because there's an infinite number of temperatures, right? As that thing expands like this, right? The temperature goes up continually from 400 to 1600, right? And so it's not even a thing. You can't even, this is, yeah, anyway, sorry. But that's okay. It's definitely